In this video tutorial, we will study the static indeterminacy of structures. Structures include beam elements, frames, and trusses. First, we must have an idea about the determinacy. Determinacy is the ability to calculate all internal and external forces using the equilibrium equation, only equilibrium equation. Let's say you have a structure. You have to calculate the internal and external forces. I have this simple supported beam with the two supports. One is hinged from leftward and on rightward it's a roller support. At hinge support, you know better that it only restrain forces in two directions, that is vertical direction and horizontal direction. On the other hand, you have a roller support, it only restrain vertical direction. In this case, for beam, we'll take horizontal as 0. Now you have two reactions, a reaction at support A and support B. You have two unknowns and a number of equations available for this beam are also equals to. Then you can calculate the number of unknown reactions using equilibrium equations because you have equal number of equilibrium equations and that of unknowns. If you have a situation like a continuous beam, like this continuous beam, in this case you have three unknowns. At roller supports and hinge support you have three unknowns. You have three unknowns and two equilibrium equations. So in this case you have a structure indeterminacy of 1 degree. And likewise, in case of frame, like you have a frame structure, you have three unknowns at this fixed support, as fixed support takes three forces like dual restrained vertical direction, force at a vertical direction, horizontal direction, and one moment. Secondly, on other support, it will only restrain vertical forces. So in this case, you have 1, 2, 3, and 4 number of unknowns. For frame, as you know that you have three equations, equilibrium equations, that are sigma f of x equals 0, sigma f of y equals 0, and sigma moment at any point equals 0. So, your structure indeterminacy for this case will be you have a number of unknowns like 4 minus number of equations or 3 equations equals 0. So for this frame you have 1 degree of structure indeterminacy. Till yet we have uh, viewed the structure indeterminacy, which is static type, static indeterminacy. We will also learn about the kinematic indeterminacy, which would be very useful in advanced structure analysis courses like indeterminate structure analysis for the calculation of a stiffness method, all types of stiffness methods. Basically, kinematic indeterminacy is related to the degree of freedom and total number of restraints. Once you have a degree of freedom at each joint and external boundary conditions and a supports condition, if you minus all degree of freedoms minus total number of restrained conditions, then we will get the kinematic indeterminacy. That is beyond the scope of this course. So will stick to the structure indeterminacy only for the beams, frames, and truss elements. So for beam elements, the total indeterminacy would be equals to internal structure indeterminacy plus external indeterminacy, static indeterminacy. Internal static indeterminacy is relevant to the basically number of elements. If you have a beam and frame with more number of elements, uh, so you have internal indeterminacy add up to the structure. Mm, the more you redundant element in the frame you have, it will induce a redundancy, degree of redundancy. So another terms pop up like what is redundancy? Redundancy is basically the degree at which um, the some structure has an extra number of elements. By removing that elements, the structure will remain stable. But in the presence of that redundant or extra element, the structure would perform redundantly or would have extra strength or stability. So um, the static indeterminacy would be relevant to the number of elements that add up to the stability. External static indeterminacy uh, is basically relevant to the support conditions and unknown reactions. Like, for example, we have some simply supported beam, some continuous beam, two span continuous beam. It has total number of external indeterminacy. Like you have a support condition like three supports and two unknown reactions, unknown equations. Three unknown reactions and two equilibrium equations. You have a 1 degree external structural indeterminacy. Uh, like we have calculated it before. For example, I induce some internal hinge upon any of the span of a beam. Let's say we have a continuous beam. Continuous beam with a hinge at its second span. On the other hand, we have a continuous beam without any hinge in either of their spans. So we will compare the uh, static indeterminacy in both of the cases. Simply, we have a static indeterminacy of 1 degree. In this case, because uh, number of unknowns are three reactions at spot A, B, C, and number of available equations are 2, 3 minus 2 equals 1 degree static indeterminacy. On the other hand, we have a internal hinge in this second span. So according to the formula, we have static indeterminacy equals the formula is 3m plus total number of reactions minus 3 into total number of joints plus internal hinges to be added in this equation. So number of members by applying hinge in second span would be 3. 3 into 3, it would be 9 plus number of reactions. We have number of reactions of 3 and 4 number of reactions are there, and minus Uh, Total number of joints are 4. 1, 2, 3, and 4. Plus number of internal hinges. There is only one internal hinge. So by this equation, 3 into 3, 9, plus 4, 13, minus 3 into 4, 12, plus 13. So we'll get 0 degree. Structural indeterminacy, static indeterminacy of this structure with a hinge in second span. So in this way we can transform a continuous beam into a statically determinate member by inducing an internal hinge. But uh, it is important to note that by the application of hinge in this span, and the stability of this beam would be disturbed. For example, you will take the moment at this hinge by considering all these forces, or considering all applied forces plus all unknown forces at this point, the moment wouldn't be equals to 0, but by the quality, by the attribute of hinge, this must be equals to 0. So this controversy stays. Because of this reason, the structure is no more stable. Now, for the case of a trusses, we have a simple formula of calculating structure, static indeterminacy. Um, there are both indeterminacy, internal and external one, but the summation of both indeterminacies will get the total indeterminacy. As we discussed earlier, that the internal structure indeterminacy would be totally referred to the um, in, to the alignment of different elements. So in case of a truss, uh, if you have an extra number of elements, adding redundancy to the truss structure, um, then the total internal static indeterminacy will be induced. Calculate the structure indeterminacy of a truss element um, by calculating internal and external indeterminacies. Internal indeterminacy is associated with the number of elements or a number of redundant elements added to the structure. External indeterminacy is totally relevant with the restraining conditions and support conditions. We have a lot number of support conditions uh, that will induce the external indeterminacy. For example, we have a truss element which contains truss. Basically, is a combination of bar elements. We have a hinge support over there and a roller support over here. And a basic requirement of fulfilling truss should be a triangular element with a good aspect ratio. That is, the least angle should be. It would be a well-conditioned truss element. Okay, secondly, we have a truss element with one redundant element adding extra stability to it, but redundancy. Um, Basically, the formula we use for calculating the determinacy is n plus r negative 2j. J are number of joints. These are only 1, 2, 3, 4, 5 number of members plus reactions, one vertical reaction, one horizontal reaction. And this is basically applied force. Number of reactions would be 3. Negative. Number of joints are 4. 8 minus 8 equals 0. We have a 0 degree of structure indeterminacy in case of truss element, um, which is which has no redundant element. For in case of redundant element which is added to it, like So you have a number of elements, like 1, 2, 3, 4, 5, and 6. 6 number of elements there. Number of members 6. Total number of reactions are only 3. And you have a joint 1, 2, 3, 4. Negative 2 into 4 joints. So in this case, 9 minus 8, you have 1 degree of structure indeterminacy, which is purely internal indeterminacy because of addition of redundant element. So in this video tutorial we have learned about trusses to determine the structural indeterminacy for both beams and trusses. So now we have an example, like we have an example of this frame which is not basically a truss. Actually the all four joints are designed as a pin joints. One horizontal force is applied at this end. So by formula, this is determinate. We have no structure indeterminacy, so but it's not stable. So in this case, it has a four number elements with four reactions. There's no structure indeterminacy in this frame, and but it is no more a stable frame. So because of the reason that it only has a reaction reserve on parallel direction, there's no horizontal restrainment because of joint conditions of member elements. So all the reactions are parallel, so it's no more stable. We have a second condition of this frame and this beam. All the reactions are concurrent, passing through some imaginary line, so it's also not stable one. Lastly, we have a beam, a continuous beam, but the support conditions are not so favorable. So the free body diagram shows that only three reactions exist. No horizontal restraint is there, so it will move like a vehicle. So it's also no more stable. Now you have an assignment. You have to determine about the structure and determinacies of all these structures. Thank you so much for watching this video tutorial.